Okay, we continue. The point that I wanted to make is as follows. If we look at the relationship between strains and stresses in general, we would find that the formulas take this form. EY is similar and EZ is similar. And if we take the particular case where the stresses are equal, then we would find that the change in the volume has this expression, right? Because this part here, I erased one, so let me just go like this and put it again. By taking this equal to that, we would find that the strain is equal to 1 over E. Sigma goes out at the integral, and then we have 1 minus 2 nu, right? And the change in the volume then, which is just this 3 times, would be 3 sigma over E multiplied times 1 minus 2 nu times the volume, right? Now, sigma greater than 0 is tension, right? So what this would say is that if nu, now consider the case that nu is equal to 1/2. If nu is equal to 1/2, then delta V would be 0, right? So this would imply that if nu was 1/2, we would apply a tensile stress in all directions and the volume would not change at all, right? So 0 change in volume. So we would normally, so based on this criteria, it is possible to say that theoretically nu has to be less than 1/2, right? So Poisson's ratio of 1/2 is actually a limit, okay? All right, so that's it. That thing, that's the oh no, one more little thing. I keep saying that's it, and then there's always one little one. The last thing is this thing about the strain rosette. Okay, and this one is for sure the last. If you think in terms of 2D, right, and you want to, let's say you have, something, and you want to measure what's going on at that point. Well, you can certainly put a strain gauge in this direction, right? Now that strain gauge in that direction will pick up what is the strain in the x direction, right? So you can measure EX. And you could put a strain gauge in the y direction, a strain gauge being simply a filament or a device that we can use to measure strains. So we could put a strain measurement in the y direction and measure epsilon y. But we cannot, just having epsilon x and epsilon y, know what is going on with the full strains, because we would need the shear strain. So the point is that with x and y, it is not possible to fully define the strain field, and we need to have the shear strain. If we have the shear strain, then we can go to our 2D stress-strain relationships and we can find whatever we want to any problem. But experimentally, the idea is, if you cannot measure shear strains, can you get it in another way? And the answer is yes. And we do that using what we know is called the strain rosette. Now the strain rosette is simply a measurement of the strain in 3 directions. So you measure the strain, let's say, in 0 degrees, you measure the strain at 45 degrees, and you measure the strain at 90 degrees. Okay? And this allows us, by the way, to introduce this idea of the strain rosette, allows me to introduce the Mohr circle for strains. So just like we have a Mohr circle for stresses, we can do a Mohr circle for strains. There are two things to keep in mind, however, and they are as follow. Gamma is positive when the positive phases have their angle reduced. So a positive shear strain is this. So if I have stresses like that, that side, these two tend to combine this way, those two tend to combine that way, this one moves in. And so the element tends to deform. See if I can take advantage of the color here. This is the undeformed element, and this tends to be the deformed element, right? So this angle is used to be 90, but now it's 9 minus the shear strain. So that's what we defined as positive shear strain, okay? But notice that positive shear strain is associated with shear stresses that are producing counterclockwise rotation shear stresses, right? Therefore, as a consequence of that, the Mohr circle for strain is one that has to be done like this. In the horizontal axis, one plots the strains, just like you would plot the stress. In the regular Mohr circle, in the vertical axis, you plot what? The shear stress. Here, the axis is done downward to take account for this difference in sign. And there is, for technical reasons about the definition of strain and so on, it turns out that we have to plot not gamma, but gamma over 2. Once you do that, then this gives you a Mohr circle for strain. So you can find the strain in any direction you want if you plot it in that form. Now, to illustrate how that is useful for the strain rosette, and I use it as an excuse also to illustrate the circle, what you have is this. So imagine that you measure epsilon 0, right? So you go like this. You measure epsilon 0 here, okay? And let's say that the shear strain was plus, and so assuming that the shear strain was plus, that would be like this, right? Now, assume that your E90, I mean, we don't know what it is, right? We don't know what this is, because we cannot measure, we only measure this. But let's assume there was something. Then we measure the 90, let's say that this was here, the E90, and that would be, of course, paired with the other one like this. Now we go like this, connect the two, that's the center, and we have our Mohr circle, right? Now, okay, so this here is the face, the X face, right? So if we want to know what is the strain in E45, we have to go 90 degrees, right? So here, this is 90 degrees, because it's twice in the circle. And so this here, if we read down, by definition, that's E45, right? Now, if that is E45, then we can say that this angle here is phi. So this angle here is 90 minus phi, right? And so we can see that, I'll just write it down because I'm sure that you guys can follow very well. this coordinate here is E0 plus E90 divided by 2, right? And that's that coordinate. So if we add, this is the radius r, so if we add the radius r times the cosine of 90 minus phi, that will be E45, right? Now it turns out that the cosine of 90 minus phi is the same as the sine of phi. Okay, cosine of 90 minus phi is the same as the sine of phi. And if you look at the angle phi, which is this one, this is phi, right? The sine of phi is equal to gamma over 2 divided by the radius, right? So sine of phi is gamma over 2 divided by the radius. And so we get E0 plus E90 over 2 plus R times, what did I say? Times the sine of phi, which is gamma over 2 divided by R. Wait a minute. Sine of phi. Oh yeah, it's just that this is not divided, this is equal to. The line got me confused there for a second, right? Cosine of 90 minus phi, this is equal to sine of phi, and sine of phi is gamma over 2 over r. So we get this, and then equal to E45, right? So the r's cancel, and we get E0 plus E90 multiplying by 2 plus gamma equal to 2E45, right? And from there we find that E45, no, not E45, gamma. We can solve for gamma as being 2E45 minus E0 minus E90. So that's it. It's a very simple thing, right? The bottom line is, if you have a two-dimensional plane, right? You want to measure you want to know what's going on at a point. So for that, you want to measure the strains at that point. But it turns out that the strain field requires that you measure epsilon x, epsilon y, and the shear strain, right, in 2D. But you don't have a device that can measure the shear strain. So what we do instead is we measure in the x, in the y, and at 45 degrees. And from this small derivation, we find that the shear strain is just 2 times whatever you measure in the 45-degree rosette, minus the 1 in 0, minus the 1 in 90. Okay? Simple enough. All right, that's it. Now, what I have left is 1, 2, 3, 4 examples. 2 of them are very simple or almost trivial, and the other 2, the third one is just slightly more, slightly less trivial, and the fourth one is the one that requires a little bit more thinking. Once I finish that fourth example, we'll be all done. So let me begin with something that is as easy as possible, right? So let's take this case, a few examples. So example 1. Let's say that we have a solid like this. Maybe this is too easy. Which is 4 inches this way, 3 inches this way, and 2 inches up. Okay? Let's say that this is point A here, this is B, this is C on the top, this is D on the bottom here. I think that's all we need. We're using numbers here, so let's say that E is 29,000 kips per square inch, and the Poisson's ratio is 0.29. Okay. Let's say that the structure is subjected to a pressure. Everywhere. So there is a pressure in all directions pushing from all faces equal to P. If you want, you can think about it as if you took this thing way down in a, or you put it in a pressure chamber and you turn the pressure on. Or you brought it down into the bottom of the ocean and you put it deep enough. In other words, you're at a place where the stress is, where there's compression coming from all directions, right? Or did I have, yes. And then it is found that that compression, that pressure, produces to a reduction on the size AB by 1.2 times 10 to the minus 3. Okay, so the question is, the first is find the pressure. Okay, it's been measured that the size AB, which used to be 4 inches, has shrunk by 1.2 times 10 to the minus 3. Find the pressure. All right, so you go to the general equations and you find. Here we don't have to say plane strain, plane stress, nothing like that, right? This is just a generic case. So from general case, we have epsilon x is equal to 1 over E multiplied by sigma x minus nu sigma y minus nu sigma z, right? In this case, sigma x equals sigma y equals sigma z equal the pressure, right? And because it's compression, it is negative, and so we have, now what is epsilon x? Epsilon x is the strain, right? So the strain is the elongation, or in this case the shortening, so it's minus 1.2 times 10 to the minus 3, divided by the original length, which is 4 inches, right? So that's the strain in the x direction. And that's going to be the 1 divided by 29,000, okay, times the pressure, goes outside, times 1 minus 2 nu, and that would be 2 times 0.29, right? And so from that equation, we solve for P, and it turns out that P is 20.71 KSI. Negative, which means compression. Okay? So, that's it, right? So we have a body. The body has a certain dimension. There is a pressure everywhere. The question is, we made one measurement, so this is just trying to have you have confidence on looking at stuff and just manipulating the simple numbers, right? So you have a dimension here of 4, that thing got shorter by how much? By 1.2 times 10 to the minus 3. Okay, so the strain in the x direction is just minus 1.2 times 10 to the minus 3 divided by the original length, that's the strain. So you know the strain, you go to your general formula, that strain is equal to 1 over E, sigma x minus nu sigma y minus nu sigma z. The stresses are the same, the pressure is the same in all directions. You take it outside, you get 1 minus 2 nu, you put the values, you get the P. Right? So that's example 1. example 2, almost as simple, just a little bit more. So in example number 2, what we say is, imagine that you have a plate, that the plate is 15 inches by 15 inches and has a thickness of 3/4 of an inch. Let's assume that in the x direction there is a stress applied at the edge of the plate of 12 ksi tension. And in the y direction there is a stress applied no, 20. Okay. Then we have the material of this thing is aluminum, which is 10 to the 4 ksi, and with a Poisson ratio of 1/3. So the first, we want to draw a circle here, which is 9 inches in diameter. The question that we want to know is if that circle is, let me see, I hope I oriented it right. Yes. So let's say that the diameter of the circle here goes from C to D, for example. So the question we want to answer is, how much longer does CD get due to that loading? Okay? How much longer? Find change of length CD. So we want to find the change of length of CD. So we say, wait a minute, this looks like plane stress, right? Because it's a thin plate, there's nothing going on in the Z direction, so I should be able to use my plane stress computations, right? So I go like this, and I say, well, based on plane stress, my strain in the x direction is equal to 1/e, this is a simplified version, sigma x minus nu sigma y, right? Then what do I have? I have sigma x is 12, sigma y is 20, nu is equal to 1/3. I plug it in and I get 5.33 times 10 to the minus 4. Right? That's the strain in the x direction. Now, if that is the strain in the x direction, how much does the diameter CD change? Well, by definition, delta of CD is just the original length, 9 inches, multiplied times the strain, which is 5.33 times 10 to the minus 4, and that is equal to 0.48 times 10 to the minus 2. So that's how much that diameter changes, right? Another question could be, how much does the thickness of the plate change? Find change of T. So if we are asked to find the change in T with the thickness, what is it that we need? Obviously we have the x, the y, this is the z, right? So what we need is the strain in the z direction. So we go to our formula in plane stress and we find that the strain in the z direction is equal to 1/e multiplied by minus nu sigma x minus nu sigma y, right? So we put the values for E, for nu, for sigma x, for sigma y, and we get, no, wait a minute, yes, and we put the values and we get minus 10.67 times 10 to the minus 4, right? So how much is the change in the thickness of the plate? It's just epsilon z times the thickness of the plate. The thickness of the plate is 3/4 of an inch. You multiply it and you get 8 times 10 to the minus 4 inches. So that's how much thinner the plate got in this particular case. Actually, I should say this was minus, so that's minus. That means it got, you know, as it's obvious, right? You're stretching it, it comes in itself. So that's how much it comes in. So those are two very simple examples. Let's take a look at the third one out of our four. The third one, I would call it integrating knowledge, or beginning to integrate knowledge, right? We've learned in this class, hopefully you've learned a bunch of different things. And we've put together some of them, and in your career you're going to put them even further, right? As you go along and you mature of these things, you will put stuff together, things that don't sit apart. But, for example, there is statics, there is structural analysis, there is the ability to calculate shear stresses from VQ over IB, the ability to calculate normal stresses and so on. These things are not computed separately, they usually come together in some form. So let's look at one case. Let's assume that you have a beam, and that beam is fixed on this side, right? And let's say it's got a load here, and I'm using, in this case, I'm using metric units. So this load is 160 kilonewtons, right? There is a cross section here. Wait a minute, is this the one I want to use? Wait a second. I think I did two examples of the same kind, and now I thought the first one. No, this is fine. Okay. So I have this. I'm interested on looking at this cross section AA. I mean at this point AA, right? And I want to know, let's say that the maximum stress in tension allowable is let's say 150 megapascals. So the maximum stress in tension allowable is 150 megapascals in section AA. Okay? Now, when I look at section AA, we are experts at this, right? So I take my bubble here, and I find that there is a shear in that section of 160 kilonewtons, and that there is a moment which depends on this distance, right? So let's say that distance is 0.375 meters, and that moment then proves out to be 60 kilonewtons meters. So now we know the shear force and we know the moment. Of course, in order to calculate stresses, I need to know what the cross-section looks like, right? So let's say the cross-section, it's an I-beam. To really be precise, I should draw the I-beam using the specific thickness and fillets and all of that, right? Well, we're going to use, let's use our often used idealized approximation in which we just represent the plates as lines that are their centers. And we accept a little bit of approximation, and we have, let's say that this plate is 204 millimeters, and that the height from center to center here is 193.4 millimeters. This is an actual cross section. The thickness of this one, the flange, is 12.6 millimeters. It's the same as this other flange. And let's say that the thickness of the web is 7.9 millimeters. Okay? The moment of inertia, I don't want to go through the calculations, but the moment of inertia of the cross section is 52.7. No, yeah, 52.7 times 10 to the minus 6 meters to the fourth. That somebody already gave it to us, so we don't have to go through the calculations, okay? You can do it, it'll be close to that. Maybe not exactly the same, because this corresponds to accounting for the actual thicknesses and so on, but that's it. So what we want to do now is we want to combine our expertise in calculation of stresses and find out what is the maximum tension in that cross-section to see if our cross-section satisfies the limit that we have imposed by design, which is 150 megapascals. So we look at this thing and say, okay, if I am looking for tension, I'm looking in the bottom of the thing, right? Okay, that's, no, I'm looking at the top because it's an cantilever, it's like this, right? So we're looking at the top. So I wonder, so I look at some points and I say, well, you know, one possibility is the stress here at the very top, A, right? That would be my over I. And another possibility, and of course there is also shear flow that's going to connect the thing. And so I can also look at this point, point B. And point B, let's say it's just the same as A, it's really high, just up there, but in the web, right? In the web. Now, because the web is much thinner than the flange, I'm going to assume, and it's true, and you can confirm it yourself later, that point B is going to be more critical than point A, okay? In actuality, it's kind of hard to talk about point A and point B in reality because the situation is like this, right? So what you have is a joint there. So stresses are clear. When we calculate shear flows, we can get them up to here, right? But what happens in the joint here is not well defined. So we can get our shear flows like this and like this, but you know, in here it's not so clear, and then here like this and so on. So I guess this point is one that you could calculate clearly, this point is one that you could calculate clearly, this point is one that one could calculate clearly, but in this idealization I'm just saying that those 3 points are really in the same place. The two on the top are A, and the one in the bottom is just B, okay? So this one is A, and so is this one, and so is this one, and this one is B. But from my idealized, simplistic drawing, I'm going to call them to be in the same location. Now, okay, so if that is the case, I'm going to say, all right, what is the stress due to bending at point B? It's just my over I, right? And so what is the moment? The moment is 60 kilonewtons meters. What is I? I'm sorry, what is Y? The distance from the neutral axis to there is half of this, right? So that would be 0.1934 meters divided by 2. And then what is I? 52.7 times 10 to the minus 6, right? Meters to the fourth. So I get meters squared over meters to the fourth, so that's going to give me meters squared. So I get kilonewtons per square meters, right? Which is kilopascals. And so if I do the multiplication, 60 times 0.1934 over 52.7 divided by 10 to the minus 6, well actually, to be more precise, I should say that, did I say kilonewtons? Yes. No. Let me be, because these units are not very familiar perhaps to everybody, let me be more like this. 60 kilonewtons is 60 times 10 to the 3 newtons meters, right? That's 60,000 newtons meters. That way I just use Newton and meters. This is 0.1934 over 2 meters. And this is 52.7 times 10 to the minus 6 meters to the fourth. So this number would be newtons per square meters, right? And that newtons per square meters would be pascals. So what that turns out to be is that sigma B is 110.1 times 10 to the 6 pascals. Or, stated otherwise, sigma B is equal to 110.1 megapascals, right? So as far as bending goes, all right, as far as bending goes, the only thing that we have at this point for bending, which is a normal stress in tension, is 110.1 megapascals. And since we are able to take 150, we may be inclined to say that it's fine. But then somebody reminds us, wait a minute, but at that location there is also a shear flow which gives a shear stress, and we know about Mohr circle and shear stresses and normal stresses combined, and maybe there is a tension that could be larger. So let's take a look. Okay, so let's do that. For that purpose, I will save my stress of 110. Sigma due to bending is 110.1 megapascals, right? Now, we want to take a look at B, and we see that we have this situation like this, right? And we want to get what's going on there. Now first, let's take a look at the direction when we were calculating shear flow. So imagine that I am looking at this cross-section, looking that way. So I take a cut and I look that way, right? So let's see, how do I explain it to you guys? So this is the 160. There's going to be 160 going up, going like that, right? And in this section over here, there would be 160 coming down. So if we are actually looking at if we cut and look at that face, what would be shear stresses coming down. So that means that the shear flows are coming like this. Okay? Those are the shear flows. So, since we are looking at point B, all right? Since we are looking at point B, we want to say, what is the shear flow at point B? So we say, okay, the shear flow at point B is VQ over I. Okay? Well, I know V is 60. I know I, it was given to us, 52.7 times 10 to the minus 6. What is Q at B? So Q at B is, we take our cut, right? So Q is that area, which is 0.204 meters, multiplied by a thickness of 0.0126 meters, multiplied times how much? The distance from the centroid of this to the neutral axis, which is 0.193 divided by 2 meters, right? And so we find that the Q at point B is equal to 2.4856 times 10 to the minus 4 meters cubed. Okay? All right, so far so good. Now that we have the Q, I'm going to have to erase here. Give myself a little room, right? And so we're going to have to calculate, but what we want is the shear stress, right? And we know that the shear stress is the shear flow divided by the width. I was going to write just T, right? But the width is the dimension that is perpendicular to the shear flow. It's equal to the thickness. So now the shear flow is going to be 160, which is times 3, times 10 to the 3 newtons, right? That's V. Times Q, which is this number, 2.4856 times 10 to the minus 4, divided by BQ over I, 52.7 times 10 to the minus 6 BQ over I. And then now the thickness for this part here, I erased it, but you've seen it before, is 0.0079. 1, 2, 3. 7.9 millimeters, right? And then that gives us 95.5 times 10 to the 6 pascals, or a shear stress of 95.5 megapascals. Okay? So we have a bending stress sigma, which is this, and we have a shear stress tau, which is this, both acting at point B, right? Now we want to, as I said, integrate, you know how? Because we say, okay, when I have a point, let's see, how do I do that? So if we have, let me see, how do I illustrate this? That's the cantilever, right? I'm going to draw it a little bit lower so that I can show the point, but basically we are talking about an element that is way up here, right? Like that. Now that element we found that has a tension stress due to the bending like this, which is sigma B, which is this number, right? Now, if you take a look at this cut here, so you can visualize the face, the load here is down like that, so that means that the shear forces here are like that, right? If you look at the other side, what remains, these forces are in the other direction, right? Downward. So that means that the shear flows here are this way. So if we look at that face of that element, I would say that there is a shear stress that way there. And then there is a shear stress this way here. That's counterclockwise, and then here is a shear that way and a shear this way, right? So our stress element that we've been looking at point B, our stress element at point B looks like this. It has 101.1 megapascals of tension, this one, right? And it has a shear that is like this, of 95, wait a minute, yeah, 95, what, 95.5, right? And then in this direction, 0. So if we now realize that our element here has this shear stresses and normal stresses, we can go and say, okay, let's look at our Mohr circle. So in the X phase we have 101 tension with 95 shear. Oh wait, what is that shear? Is it plus or minus? It won't really matter, but I should be consistent drawing it, right? So we have 101, and this, in our Mohr circle, we would plot the shear of that phase negative, right? Because it's counter. So I would come here and say minus 95.5. Then on the other phase we have 0 and we have 95.5. Then we join the two for our Mohr circle, that's our center, right? And that center is going to be 55.5, right? Because it's half of the 101. And this radius from here to here is 55.5, and from here to here was 95.5, so the radius is the square root of 55.5 squared plus 95.5 squared, right? And it turns out that I didn't write what it was, it's just the radius. But what I can say, I just wrote what the sum was. So you can see that now we take the Mohr circle and this thing will go like that. And right here we'll have sigma max, right? And sigma max in tension is going to be 55.5 plus, right, the radius. Where the radius is, so we have sigma max is equal to 55.5 plus the square root of this dimension, which is 55.5 squared, plus this other dimension, which is 95.5 squared. And it turns out in this case that it is 165.3 megapascals. So, what do we conclude? We conclude that even though the bending stress was less than the allowable, it was only 101, when we computed the shear stress and we accounted for the fact that the shear stress and the bending stress combine to give us stresses in inclined directions, that there is an inclined direction where there is a tension that is bigger than the allowable, and so we would have to say that the beam as presented does not satisfy the constraint of 150 megapascals allowable stress. Okay? Let me go over that without numbers one more time. Our beam is like this. It has a load here. In shape-wise, it's like this. There is a thickness here, T1. There is a thickness here, T2. And there is a thickness here, T1. We are looking at some cross-section here. And there is a distance, let's say, N. And this is P, right? So we found that the shear is P at this cross-section, and that the moment is Pn, right? We don't get lost in the numbers. So we have the shear at the moment. We found from the moment that at this point B, which is very high, essentially in an idealized sense is on the top, this being H, that this moment gives me a stress at B of tension, which is equal to Pn, which is the moment, times H over 2 divided by I, right? So that's the tensile stress that I get at that point. That means that this element, which is here at that point, actually no, this element, which is here, is being pulled like this with sigma B. That little element, let me see if I can draw it. It's kind of hard to draw it for me. That element is kind of like that there. It has the tension like this now. Okay? And when I looked at this part here, and I saw this, and I saw that, then I looked here, and then this is down. So that means that here we have a shear stress that is down like that. Okay? From the shear flows, which are coming in like this, and then they head down this way, and then they head out this way. That element right there, then we said, okay, what is this shear stress tau? And then we said, okay, well the shear stress tau is the shear flow divided by the thickness. The thickness at that point is T2. And what is the shear flow? Is VQ over I, T2, right? So we know I, and then how do we calculate the Q there? Well, the Q there in the cross section is just, if that distance is Z, then the Q is just Z times T1 times H over 2, right? Because I take a look at this cut here, and that's my Q. So I put it in here, and I get a shear stress, right? I put my Q, I put my I, and so on, and get a shear stress. Then once I know the shear stress and the sigma, I have a more circle problem with sigma, shear, 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 right? We know sigma, we know tau. That problem is a more circle problem. To find what is the maximum tension, so I go with my sigma and my negative tau, and I go with my 0 sigma, my positive tau. So like this, find the radius, make the circle, this is the maximum tension, right? And that's what we have to compare to the allowable. That tension is not in this direction, is in an inclined direction, right? At that point. All right? Okie dokie, that's it. So we have one last problem. One last example to illustrate.